bit of time to get inside the room. Okay. Okay, I think we can start. Okay, good morning, everyone. Thank you to be here to the fourth day of the TREX summer school. Here is the agenda of the day. So we will start with a lecture from Michele Casula that is going to talk about the diffusion Monte Carlo. Then we will have our usual coffee break from 10:30 to 10:50. And then we will move on with the second lecture, also made by Michele Casula, also about the diffusion Monte Carlo. Then we will have our lunch break from 12:30 to 1:30, and then we will move on with the third lecture of the day made by Kosuke Nakano. And then from 14:30 to 4:30 p.m. we will have the hands-on session, as always. I want to remind you to apply to the poster competition. If you didn't have time to do it, please upload your poster, and there are amazing rewards and prize that you can win. I also want to inform you that tomorrow we will have the picture with everyone. So if you can please join during the coffee break. If you want to be part of the picture, you can just turn on your camera and we will have a picture with everyone. And I want also to inform you about this news. We will give you the possibility to download the TurboRVB code in your computer. You just have to sign in and follow the link that I will share with you in the chat in a few minutes. Okay, now I want to leave the floor to Michele Casula for his first lecture. Thank you, Michele. The floor is yours.
Okay, thanks, Jacopo. Okay, so yes. Okay, so can you see it? Yeah. Right. So good morning, everyone. So the outline of today's lectures is the following. I start by introducing and explaining the diffusion Monte Carlo method. I'll go through another projection method, which is called power method, and I'll extend the power method to the continuous case by talking about the lattice regularized diffusion Monte Carlo. Okay, so again, as Sandro explained to you the day before yesterday, by talking about the variational states we developed in the TurboRVB code. Our main goal is to look for the ground state of a Hamiltonian H. And we look for this ground state by trying to minimize the variational energy of a trial state, which can be which is our variational wave function. So this is basically the the task we'd like to accomplish to find the minimum of psi h psi over the wave function psi belonging to the Hilbert space. So we have a variational freedom in choosing psi, and in Quantum Monte Carlo, psi, as we have seen, is a complex many-body state, which includes, which encodes correlations in a very smart way. And so for all these wave functions, the variational principle applies, which states that all these wave functions will have an energy which will be an upper bound of the true ground state energy of the system, of the Hamiltonian. So by getting closer and closer to the ground state energy, we improve our psi, and the ground state will have, of course, the ground state wave function will have, of course, the ground state energy as variational energy. So there are different methods to look for the ground state, or to optimize in general the wave function. And we have seen that Sandro yesterday talked about the optimization method. So in the case we have psi including variational parameters in a variational form, there are methods to find the best parameters which minimize the expectation value of the Hamiltonian over the trial wave function. So this is a way to go to find the best variational parameters. There is another way, which is called basically projection. So you project the initial wave function psi to the true ground state of the system. So the stochastic projection can be seen as, if you like, a black box optimization method, which is done by some stochastic process which is developed in a proper way. So this projection method is based on a green function, by applying a green function to our variational state. And the green function is an object which will fulfill the time-dependent Schrödinger equation written in the imaginary time. And so the idea of this family of methods is to iteratively apply the green function to an original variational state, such that this green function will filter out higher energy states, and you'll end up with, hopefully, with the ground state of the system. So you see here that there are basically two categories. So one is the one based on a variational, a parameterization of the wave function with given parameters to be found optimal. And the other one is sort of a blind process, which takes an initial guess and projects this initial guess towards the ground state. So both methods are meant to find the best variational state, and by the best variational state, I mean the one which is the closest to the true ground state of the system. So, the green function here can be defined in several ways, and there are two main ways to define the green function. And the definition of the green function used to project the initial tri-wave function defines also the specific projection method used. So the idea of building up a green function is to construct an operator, the green function, which inverts the spectrum of H. And so there are basically two main green function operators. One is this exponential of minus tau H minus ET, this exponential form, and this will give rise to the diffusion Monte Carlo method. And the other one is lambda minus H as green function, and this will be basically the heart of the power method. So diffusion Monte Carlo. So imagine that you have a variational state, psi naught, and then you apply the exponential of minus tau H minus ET. So how can you show that this will lead to, this will filter out the high energy states? So I can switch to the tablet, maybe. So we have our green function operator, which is defined as e to minus tau H minus ET. Okay? And so we'd like to apply iteratively G over the initial guess. So we have an initial guess, initial trial wave function. And by this trial wave function, that's a sort of jargon. It's, if you like, your best guess. Okay? Your best guess. For the ground state. Of course, the ground state is unknown, so that's basically the challenge we are faced with. And this initial trial wave function can be taken as the best variational state we optimized previously. Okay, so usually the initial psi 0 is your best variational wave function optimized at variational level. Now, we'd like to apply n times this operator G on your wave function, on our wave function psi naught. So, and the resulting wave function will be called psi n. And so this will be G operator applied n times to our starting wave function psi naught. Okay? So this will be equal to e to minus n tau H minus ET applied to psi naught. Now, this operator here can be written in terms of a density matrix. So it's basically the evolution operator is the evolution operator in imaginary time. So this can be written in terms of the eigenstates of the Hamiltonian. So imagine that. So we imagine that I know the spectrum of the Hamiltonian, which is something I don't know really. But for formally showing that these projects that we function towards the ground state, I assume that I know the spectrum of the Hamiltonian. Okay, so I imagine that I assume I know the spectrum of the Hamiltonian, and I call psi I the eigenstates of the Hamiltonian with energy EI, eigenvalues EI. And so then I can write this projection operator as a density matrix. So sum over the eigen states psi I, e to minus n tau, EI minus E trial. So E trial is an energy shift, okay? So I haven't defined very well this. It's an energy shift, which can be defined arbitrarily. And you're gonna see how it's defined. And then you have a density matrix developed on the eigen states. And you should apply this to the psi, sorry, the eigenstates have the apex I to be distinguished from the initial wave function psi naught. Okay, so now imagine that you apply this operator G n times. Okay, and imagine that you tune ET to be the ground state of the system, so to be in this notation E naught. Okay, you tune this, and then you let n go into infinity. So you apply many times the projection operator. What you get so you can see that you're going to have exponentials of e to minus n tau delta E I. Now delta EI are equal to EI, the eigenstate of the ith state, minus E naught, the ground state. So those will be non-negative. And so for, let's say the ground state is not degenerate, for I greater than 0, so I not the ground state, these exponentials will go exponentially fast to 0 in the limit of large n. Okay? And so in the limit of large n, you take this limit, the only term which will survive will be psi naught, ground state, psi naught, psi initial. Okay? And so indeed this green function projects out the initial state to the ground state, provided the overlap, that's a very important observation, the overlap of the initial state with the ground state is not zero. Okay? Provided psi naught, psi initial is different from zero. Okay. So basically, this is the last line of this slide. In the limit of n infinity, you project out the ground state psi naught. Now, we can rewrite this application of this projection operator, e2 minus n tau h, in an integral form. Okay, so we work in the phase space of electron coordinates r, and so we should translate this application of the projection operator to psi naught into an integral form expressed in the basis set of spatial coordinates, capital R. And so we have to express also the projection operator in the basis of electronic coordinates. And this is a formal way to express the green function operator e2 minus tau h into the phase space of electron coordinates. So, do we know the form of G? So this is a question. Do we know the form of G? So to answer this question, let's again take the imaginary time shadowing equation G should fulfill by definition. So G should fulfill this equation here, okay? And of course, the important point is also to define the initial conditions, because if you don't define it, that's basically a differential equation. So the solution is defined only if you define also initial conditions. And let's assume that the initial conditions for our green function is a delta function. So basically, it means that at a 0 time step, you represent the initial psi, your best guess for the ground state. Okay? So that's the initial condition. And then we'd like to know what is the form for G in order to further project psi to the ground state. And the underlying question also is, can we see this convolution between the green function and psi as a stochastic process? Can this convolution equation be implemented stochastically? Because finally we'd like to project psi in a stochastic way. So to understand whether this convolution equation, this integral equation, can be implemented stochastically, we need to know the form of G, first of all, okay? So let's see if we know the form of G. So assume that now the Hamiltonian H is only made by the kinetic term. So H is written as kinetic term plus potential, right? And assume for the time being that we set the potential to 0 and you just keep the kinetic term K. So do we know how to solve this imaginary time scheduling equation where h now is just the kinetic term. So the solution is yes. We do know the answer is yes. We do know the solution of this equation, and the solution in the case v is 0 is the exact solution for the green function is this one. It's a Gaussian whose spread is square root of tau, and so the spread, if you like, increases with the time evolution. So it's a diffusion process where at the time 0 time, your particle is centered at r naught, and as the time evolves, the probability of finding the particle which is diffusing in the space, it's given by the Gaussian probability with a spread which increases as square root of tau. So we can actually prove this relation. So I can again switch to the whiteboard. So, right. So we'd like to solve this equation here. So h times the green function equal to minus d sub dt, the green function. Now h, so this depends on, let's say, depends on r. Okay. So h now is just the kinetic term. We don't have the potential, so it's minus 1/2 nabla, the Laplacian. So that's in Hartree units, okay? So I don't know if you are familiar with the Hartree units. So the Hartree units are such that E squared equal to 1, H bar equal to 1, and the electronic mass equal to 1, okay? So if you write the Hamiltonian in the Hartree units, the Laplacian is minus 1/2 nabla squared. So so this form here is a shortcut to include n particles, n electrons, okay? So now the Laplacian, my Laplacian here is a shortcut for a sum over all the particles in the system of their Laplacian. Okay? And also R, my capital R, as I wrote before, is a 3-dimensional vector including the coordinates for all n particles, where R1 is the coordinate of the electron 1, and so on and so forth. Okay, so what I'd like to show is that the solution of this equation here is the following. is G of R is given by one over 2 pi tau. Let's call it T. It will be clear. My tau is not that elegant. T to the 3/2 n times e to minus r square over 2t. So in fact, this g of t depends both on r and t. So this is something one should keep in mind. Okay, so it's the time-dependent solution, the solution of time-dependent Schrödinger equation. So it depends on both r and t. And this is normalization factor for the Gaussian. Okay. Okay. Now, so let's prove that this is a solution of the time-dependent Schrödinger equation. So I have to now to compute the minus 1/2 Laplacian applied to G of RT. So the prefactor depends only on the time, so I can just pull out of the derivation. And so I have to compute the Laplacian of e to minus r square over 2t. Okay. So in general, I can write this as a Laplacian of a radial function. So this depends only on the modulus of R, right? So I can write the general formula for the Laplacian applied to a function depending on only on the module of R. And so this will be equal to n d minus 1 f prime divided by r plus f second of r. So you can derive this by applying by exploiting the fact that this is a radial function, and by knowing, for instance, that so an intermediate step will require the divergence of R vector over R modulus. and this is equal to n d minus 1 divided by r, where now d is the dimension of the system, dimension of the space. Okay, so in our case, d equal 3. Okay. So, now, then you have to compute f prime of r and f second of r. So f of r is defined this way: e to minus r squared over 2t, right? So it's the Gaussian. So f prime of r is equal to minus r over tau times e to minus r squared over 2, t. Minus r, so let me make more space here. Okay, so this is f of r. Now f prime of r is equal to minus r over t e to minus r squared over 2t, and f second of r is equal to r squared over tau over t squared minus 1 over t e to minus r squared over 2t. Okay, so if you plug now f prime and f second in this relation, you will get the following. You get minus 3n divided by t times e to minus r squared over 2t plus r squared over t squared times e to minus r squared over 2t. So this is for the Laplacian part. And then for the time-dependent part, so we should compute the derivative of g with respect to t. And so keep in mind that g of RT has two factors depending on t. So one is the normalization factor. So it's, as I told you, 1 over 2 pi t to 3.5. And the other one is the Gaussian exponent depending on t. So by deriving this derivative here, you should have two contributions. You get two contributions. One is from this, and the other is from the other factor here. Okay. And so you get this result for the derivative minus 3 n 1 over t plus r squared over 2t squared times g of RT. Okay, so this is the derivative of g with respect to t. Okay. So you see here, that's the derivative, the time derivative. And this is the spatial derivative, the one we derive here. Okay. And so so we got now, so if we translate this Schrödinger equation, so we get minus 1/2 Laplacian of g equal to minus the time derivative of g, and you have minus 1/2 factor here and minus 1 factor there. So if you put the 1/2 in front, because we just this was just the Laplacian of g. So if you put the minus 1/2 in front, you realize that this 1/2 in front will result into 3/2 here and r squared over 2t squared there. And so by comparing the two sides of the equation, you see that -1/2 Laplacian of G is equal to the time derivative of G, right? So then it means that we prove that this form, the Gaussian spreading with variance square root of t, is the solution of our time-dependent Schrödinger equation in imaginary time. Okay, so, and the key point to show this equivalence is to recall that not only the Gaussian has a time dependence, but also the prefactor here, the normalization. So when you derive with respect to time, you have to pick a contribution also to the prefactor, the normalization prefactor here. Okay. So now the other case is the case where the potential is V and the kinetic term K is equal to 0. So in that case, we have this equation here for the Green function, and this is easily proved that the solution for this Green function is an exponential having as exponent minus tau v of r minus et. Okay, so this is the solution of this equation, where the Hamiltonian is just the potential term and k is equal to 0. Of course, here I recall you that the initial condition is such that at t equals 0, r prime is equal to r. So that's basically is the initial condition, and the exponential is the solution of this equation, which is straightforwardly seen by deriving this G with respect to time here. Okay, so what are the meaning of these two extreme cases? In the case of zero potential and a pure kinetic Hamiltonian, I have a diffusion process, okay, and of a particle spreading, of a particle, but also a set of particles. So we have now n electrons here spreading with the Gaussian form. And for the case of a pure potential, a zero kinetic term, I have a process of a weighting process. So where, I mean, it's called also decay process in nuclear physics. But anyway, so this is a decay process governed by this weighting factor, E2 minus tau V minus ET. Okay, so what is the meaning of this term? This term, this weighting factor here, will enhance, will put more weights on situation where the potential V of R is low, and will suppress configurations where V of R is high. So it's basically, it weights the walker. So now it weights this, let's say, a state given by the configuration capital R according to the potential, by favoring situations where the potential is low, and by suppressing states where the potential is high. So now the Hamiltonian is now K plus V. So we have to evaluate not the two extreme cases, but the two cases together. So we have this E2 minus tau K plus V operator. And this is hard to, not possible to evaluate exactly, because K and V does not commute. And so we have to split K and V into two factors, plus what is left. So we approximate the full potential K plus V into a product of two factors, two operators, but this is an approximation. Okay, so we break up, so that's called throttle breakup. So we break up the operator into factors by making an approximation of order of tau square. So one can show that this tau square, which is left, basically depends on the commutator of between K and V. So the error we make is proportional to both tau square and the commutator between K and V. If the K and V commute, we don't make any error, but that's not the case here. So it means that the throttle breakup, the approximation is getting milder as I reduce the time step. So if tau is small, the approximation is milder, because the term which is left is of the order tau square. So the idea is to combine the two extremes, so the potential, the pure potential and the pure kinetic process together as a product of the two green functions, separated green functions, which is, if you like, the best I can do in principle with the knowledge, the exact knowledge of the two independent processes. And this is an approximation. It is an approximation, which is a short time approximation of the green function. And therefore, if I build my stochastic process based on this green function, this stochastic process will be affected by the approximation made in the throttle breakup. And to get the right result, the unbiased result, I will have to extrapolate my stochastic process in the vanishing time step limit. Okay, so now you can see that as I take this, the short time approximation, and I repeat applying this green function many times to my initial wave function, this repetition, this series of events will have a dynamics, and this dynamics will have a time step. So this tau now is called time step because it sets basically the time frame of each iteration in the green function in the diffusion process. And this time step should be taken small enough such that the bias is not that large. And I should, in principle, repeat the calculations for different time steps and extrapolate my results in the vanishing limit for a time step. So we can solve, this is an approximation which is controllable, right? So I can repeat the simulations with different time steps, and I can extrapolate for vanishing time step. But anyway, so at this stage, I have a problem with my green function. I still have a problem with my green function, apart from the problem of the time step, which is controllable. The problem is that the potential now diverges when two electrons get close, when two electrons overlap. So we have widely fluctuating weights. And so this will make my algorithm unstable. So I should cure for these wild fluctuations of the potential. So I need to improve the algorithm. And this is basically, for the time being, it's the worst, a very bad situation. So I was able to write the green function in a proper way. But the way I came up with has this severe problem of having the weights widely fluctuating due to the fact that the potential, the Coulomb potential, is diverging when two electrons coincide in space at the coalescence points of two electrons. And so this is typical of basically how ab initio Hamiltonian, so other Hamiltonians could have potentials much more well behaved, but the ab initio Hamiltonian has this difficulty of having diverging potentials. So what is the solution for these divergences? The solution is to modify the green function and to use what's called an important sampling technique, important sampling strategy. So I start from this integral equation, which is my diffusion equation, which projects the psi to the ground state, and I modify psi n, so my nth iteration for the wave function, with by multiplying this by the initial trial wave function. Okay, so again, trial wave function in this jargon means the initial wave function in my projection process. So instead of now propagating psi n, or psi n minus 1, I'd like to propagate psi n times the initial wave function, psi trial. And so I have to rewrite this integral equation by finding the corresponding green function, the new green function, which propagates, instead of psi, the product of psi times the initial state, and I call it as f. Okay, so formally, this modified green function, which propagates f instead of psi, can be written in this way here. And so everything goes in the same way. So and the way I mean it's very easy to derive this relation by multiplying the right-hand side and the left-hand side by psi trial. Okay, so if you multiply the right-hand side and the left-hand side by psi trial, you realize that the green function, the new green function which propagates f instead of psi, should have this form here. Now, it means that this green function propagating f will project f to the distribution, which is not anymore the ground state, psi naught, but it's the ground state times psi trial. Okay, so this will be the large projection time limit, and this psi naught times psi trial is called a mixed distribution. It's not a pure wave function, but it's a product of the projected wave function times the trial initial wave function. So why I'm doing this? Again, I'm doing this to solve the problem of the divergence of the potential appearing in the weighting factors. Indeed, the green function, now g tilde, which is now g, which is the important sample of the green function, has a different form with respect to the original one. And the differences are twofold. One difference is the presence of this additional term in the diffusion process, which is the drift, called its drift velocity. So it's the gradient of psi over psi. And the other difference is in the weighting factor. So the weighting factor is no longer depending on the bare potential V, but instead of the V of R before, this has been replaced by the local energy of R. Okay, the local energy at the position R. Again, R, as I told you, is the many electron coordinate. And so what we have gained from doing this? Well, the drift velocity has an important role because it pushes the walkers away from the nodes. Okay, so it pushes the diffusion process to regions of large psi trial. Okay, so now I'm using the word walkers because I'm building a Markov chain based on the iterative process of applying the green function to the initial state, and this Markov chain can be seen as a path in the electronic position space. Okay, so and that's why I call this a walker. So the walker is the Markov chain developing along a path in the space in the coordinate space for the electrons. And what are the nodes? Because I'm also talking about nodes here. So also the nodes should be defined. The nodes are a surface, an hypersurface of the 3n-dimensional space of the electron positions, where the wave function is 0. And we know that there are nodes in the ground state of electronic fermionic wave function, because the fermionic wave function must fulfill the quantum statistics, so must be antisymmetric by permutation of electrons. So these will create nodes in the space of the electron coordinates. And so the nodes are, again, by definition, hypersurfaces in the electronic configuration space where the wave function is 0. So those are defined by the zeros of the wave function. And so the drifted velocity will push the electrons away from the nodes, because it will pushes the walkers towards directions where psi trial is large. So this is one effect of the drift velocity, and then there is another difference with respect to the previous green function, which is the replacement of the potential, the bare potential, with the local energy, and that was the original reason why we went to the important sample green function from the bare green function. And so now, why the replacement of the potential by the local energy makes the algorithm more stable? So this is something you should know, because Sandro, the day before yesterday, explained to you an important property of the tri-wave function, of the variational wave function, which is the fulfillment of the cusp conditions. I hope you remember what Sandro explained to you. So the wave function, a good variational wave function, is such that the divergence in the potential coming from coalescence, the coalescence positions of two electrons or one electron and one ion, which basically implies the divergence of the Coulomb potential. These divergences are compensated by the kinetic term. Okay, so the kinetic term applied to the tri-wave function will compensate the divergence coming from the potential, such that the local energy, which is the kinetic term plus the potential, does not diverge at the coalescence points, at the points where electrons, two electrons are overlapping, or one electron and one ion are overlapping. And so, thanks to the property of a good variation wave function, which is our initial guess, and thanks to the fact that the important sample green function will have the local energy instead of the potential in the weighting factors, this will make the algorithm stable. Okay, so by going from the evolution of psi, the projection of psi, to the projection of the mixed distribution, psi times the initial psi trial, I've been able to make the green function an object which basically describes a diffusion plus drift in the kinetic part, in the kinetic prefactor here, and a weighting process and decay process, which is stable because thanks to this modification of the green function, we replace the bare potential with the local energy, which is well behaved even in the coalescence points of the configurational space. Okay, so now I solved also the problem of the stability of the green function, and so this can be interpreted as a stable stochastic process, right? Because it's positive definite, so there is no sign change here, and it's stable because the weighting factor is cured. So it means that I'm able to solve the many-body problem, right? So apparently I came up with with a projection method, which is able to project the initial many-body wave function to the true ground state, which is stable, which can be implemented stochastically because G R prime R is positive definite. And so what is the missing point here? Okay, so if these were true, I would have solved the many-body problem, which is not the case yet, because it's still an unsolved problem in the many-body field. So what's missing in this description? Well, what is missing is the fact that my electrons are fermions again, and so it means that the green function is positive definite within a nodal pocket, but if I go back, if I take this definition here of the important sample green function, you see here that this green function will have a sign which will depend on the relative sign of psi trial at R prime and psi trial at R. So the green function will change sign as my walker, so my chain, my random chain, my Markov chain will cross the node, because if it's the case, the sign of psi trial at R prime will be opposite than the sign of psi trial at R. And so we'll have a sign change with a minus sign. And so this will, it means that for fermions, the important sample green function is not positive definite. So I should make a further approximation to make this green function positive definite. So what is the further approximation I should make? The further approximation, it's called the fixed node approximation. So my diffusion process will be constrained to evolve within a pocket of the many-body wave function. So what does it mean, pocket? A pocket, a nodal pocket, is a region of the electronic configuration space where the wave function has the same sign. So a nodal pocket is, of course, limited, is wrapped by the nodal surface. So the nodal surface will wrap pockets of different sign. And as long as the diffusion takes place within a single nodal pocket, there is no sign change. And so the green function will keep the same sign, and I can interpret the green function as in a stochastic way as a probability to move from R to R prime. And so I can build a diffusion process on this green function constrained on a given nodal pocket. So what does it mean that I keep the evolution within the nodal pockets? First of all, the nodal pockets, how can we define nodal pockets here? The nodal pockets are those of the tri-wave function, right? So remember that the important sample green function will have sign changes defined by the sign flip of the tri-wave function. So it's the tri-wave function which will set the sign of the green function, of the important sample green function. So I will constrain my diffusion process to take place within the nodal pocket of the trial initial guess wave function. And so it means that I impose that also the nodes of the projected wave function will have the same, will be the same as the ones of the tri-wave function. I won't allow for a nodal surface relaxation in the diffusion process. That's why it's called fixed node, because the nodes of the projected green function will be the same as the nodes of the initial tri-wave function. So this diffusion will have boundary conditions imposed by these constraints, so given by the tri-wave function. And so I'm solving a differential equation with not the best boundaries conditions, if you like. So I put constraints, so I would bias the result. If the nodes are not, if the nodes of the initial wave function, the tri-wave function, won't be the exact nodes. In the case the nodes of the initial wave function were exact, I wouldn't get any approximation by constraining the diffusion within those nodes, because those nodes will be the right boundary conditions for the problem. But the knowledge of the nodes of a wave function is, if you like, is not exact, in the sense that the nodes are not known. The nodes of the ground state are not known a priori, okay? And they are only known in some particular situations, like one-dimensional systems, where the symmetry of the antisymmetry of the Hamiltonian will lead to a set of conditions which will determine completely the nodal surface. And this will happen only in 1D. While in 2 dimension and in 3 dimension, the conditions, the antisymmetry conditions, won't be enough to fix the full nodal surface. In any case, the fixed nodal approximation gives an upper bound of the true ground state energy. So the energy I obtain by projecting the initial wave function with a fixed node green function, this projection will lead to an energy which will be variational, so will be greater or equal than the true ground state energy. I still have a variational approximation in place. Okay, so now let me make some further comments on the stability of the algorithm. So now we have seen that we are able to construct a stochastic process based on importance sample green function. This stochastic process must be constrained within the nodal pockets of the initial guess, and this will make an approximation, which is called the fixed node approximation. We have also seen that the green function is written thanks to a throttle breakup of the full projection operator. So we still have also an approximation in time step, but this, as I told you, the approximation in time step is controllable by a time step extrapolation. So I need to run several calculations, at least 3 or 4 calculations, different time steps, to extrapolate the energy. And this will be, anyway, an extrapolation which will give an upper bound of the true ground state energy. Now, there are improvements upon this algorithm, which are given by modifications of the drift velocity on the weighting factor. Okay, as I told you, we cured the divergences, the wide divergences of the bare potential, but we still have divergences around. So one divergence, for instance, is given by, so if you take the drift velocity, there is still a divergence at the nodal surface here of the tri-wave function, because here we're going to get a zero if R lies on the surface, and this will lead to an explosion, a blow up of the drift velocity. Okay. So this will make the algorithm sort of unstable, although the instability is less severe than the one we have seen before for the branching factor of the bare potential. But this will affect the behavior as a function of a time step. So, there's been an attempt since the beginning to regularize these terms. Like the drift velocity here, by playing with cutoffs. Okay, so one cutoff which has been proposed to avoid the divergence of the drift velocity is to normalize the actual velocity by a factor which is time step dependent and also dependent on the actual magnitude of the drift velocity. So if the drift velocity is small, then the renormalized, the regularized velocity will be equal to the true velocity. If the velocity, the quantum force, is large, in that case, the renormalized drift velocity will be damped by this factor here. Okay, there are arguments how to build this renormalization factor. Okay, and you see here that this renormalization factor depends also on the time step. So the smaller the time step, the lesser, the milder the impact of this renormalization. Okay, these divergences occur because we still have a dynamics which is approximated by the time step, if you like. And the same sort of cutoff can be applied to the reweighting factor, which is also branching factor. And so this basically leads to the product of V bar over V applied to this weighting factor, and this V bar over V diverges compensated divergence of the local energy at the nodal surface. Okay, so let me explain why you still have this divergence of the local energy. So I told you that we cured the divergence of the bare potential. Okay, and so the behavior of the local energy is fine at equidistant points, and so where two electrons are together. Okay, but we have still divergences in the local energy, where in the case where we have nodal, in the case where psi tri is 0, so on the nodal surface. So we still have some divergence present in the local energy, okay, which goes like 1 over R in that case. To cure that divergence, one can multiply the local energy by this V bar over V, which has the right dependence close to the node to compensate the 1/r divergence. So there's an improvement also on how to dump these divergences by recent work by Sandro and also other people who contributed to TurboRVB, like Andrea Zen, and so they improved these cutoffs such that the algorithm is size consistent. So if you have two fragments far apart, the dumping of these reweighting factor is such that you recover the energy of two independent systems. Okay, so anyway, so those are the improvements on this cutoff, both in the drift velocity and also in the reweighting factor. So let me conclude this part of the lecture by reminding you the importance of a multi-walker approach in this algorithm. So you can in principle have a single walker, single random walk Markov chain, propagating, so diffusing and being weighted. Okay, so by these two contributions of the green function, the diffusion part times the reweighting part. But this will lead, if you keep evolving the chain, this will lead to large fluctuations in the weights, because the weights, the total weights are the product of these branching factors, where each factor is a single time step. So by accumulating the factors, you get final products which can be strongly fluctuating and make again the random the Markov chain unstable. So to avoid the or at least you get, if not unstable, you get large error bars in the averages. So to get these fluctuations stable, you use a multi-walker algorithm. So you propagate in parallel many Markov chains, and it's at every time, branching time, called branching time t, you'll sort of reconfigure the walker population. Okay, so imagine that after propagation of time t, made of course many time steps of time steps tau, you'll have you have the set of chains of walkers you let evolve, having weights Wm, okay, well, Wi, okay, where I now is the index of the walker. So you can have different situations. So you can have a situation where Wi are very large or Wi are very small. And you'd like to keep the population having the weights as stable as possible. And by saying the weights as stable as possible, the weights not fluctuating too much around the mean value. So after an evolution time t, you'd like to reconfigure all your walkers or your chains such that after this reconfiguration, all walkers will have, again, weights equal to 1, okay? And so the reconfiguration makes the algorithm more stable and is done such that the walkers are spawned or killed according to their weights after this branching time t, after this time frame t. And this is called the branching step, okay? and you can see here now that if you like, the reweighting factor is a sort of death-birth process at the end, because if the weighting factor basically leads to
Ele, you are on mute. You are mute, sorry. You have to unmute yourself.
I was muted.
Yeah.
Sorry.
And 32, so I don't know if you have...
I'm gonna finish this part, okay?
Okay.
So, this will lead to the the spawning of the walkers, or vice versa. If the weights are too small, this is gonna kill the walkers. So after the reconfiguration, the walkers will be either spawned or killed, and they all have weights 1 till the next branching time t, where again another reconfiguration will occur. So in this way, the evolution will be more stable, and thanks to the multi-walker implementation. So in diffusion Monte Carlo, the multi-walker implementation is critical to make the algorithm stable, much more critical, if you like, than variational Monte Carlo, where in that case the walkers are really independent. In diffusion Monte Carlo, they are not, through this branching step, which will basically reconfigure the population, and so will imply some transfer of walkers across processors, because the strategy we have in TurboRVB is that basically a walker is handled by an MPI process. And so if the walker is spawned, then the information of the walker, namely the position of the walker, should be transferred to another MPI process, which will take the child, if you like, the child of the process, the walk which is spawned. Okay, so this branching step will imply some MPI communication and some interdependence between the walkers, which is absent in variational Monte Carlo. So let me finish with this slide here. So that's basically the summary of the diffusion Monte Carlo algorithm. We sampled the walkers, so the random chain is sampled at the beginning based on the initial tri-wave function modulo squared, and so the green function, which will project the trial state to the ground state, will have a diffusion plus drift process, which will define now the proposal probability T in the generalized metropolis algorithm. So if you remember, the first day we have seen the generalized metropolis algorithm, which also requires, which will allow for a proposal probability. Okay, and this proposal probability is the one of the drift diffusion process. So we'll apply this, we'll propose a new position R prime according to this diffusion drift process, and we'll apply the fixed node approximation to this new position. So if this new position, if the wave function, the sign of the wave function at new position is opposite to the sign of the wave function, the starting position, will reject the move. So this R prime should stay in the same nodal pocket of the wave function. And then if the fixed node approximation constraint is fulfilled, we reject or accept the new move R prime, according to the Metropolis algorithm rule. Okay, the acceptance probability given by the Metropolis algorithm. And so we evolve now the walker. So we have the new position for the walker. So we accept or reject. So our prime will be now defined, and then with the new R prime, will, after this new R prime is set, will update the branching step according to the so we will update the weighting factor according to the new weight of the walker. So E2 minus tau V of R minus the drift minus the shift energy. And so after iterating several times this diffusion reweighting process, when the total time will hit the branching step time t, then we'll perform a branching step. Branching step with the spawning and killing of the walkers, and then when the branch reconfiguration, the walker reconfiguration is done, we'll then keep iterating again the drift and diffusion plus reweighting, and so then we iterate drift, diffusion, reweighting, and branching many times, and this will lead to the projected distribution, which is a mixed distribution. The projected distribution wave function times the initial tri-wave function. So I stop here.
Okay, perfect. So let's everyone come back maybe at 11 this time. So we will have 20 minutes break. Let's rest and then let's come back at 11. Bye everyone. See you later.
Bye-bye.
Okay, welcome back everyone. We will start with the second lecture made also by Michele Casula. So if you want, Michele, you can share your screen and start. Michele, if you want to share your screen and start, you can whenever you want. Michele, if you want to start, you can.
Yes, okay. So I think it's time to resume. Before proceeding with the lecture, I'd like to ask you, all the participants, if they have questions about the first part, about diffusion Monte Carlo.
Absolutely. If you guys have questions, please.
Yeah. So don't be shy. I mean, we are facing a very hard, situation. I mean, lecturing online is much harder than lecturing in presence. So if there is a feedback, also I think it's beneficial for everybody. So yeah. So if you have questions, so if you didn't understand some parts of what I presented, please feel free to ask, because this will be beneficial for all the attendees, all the participants. There is a message. No. Okay, yes, in the chat I have some questions. So is capital V for the regularization of the branching factor the same as the drift velocity small v? Yes. So let me open again the PowerPoint. Here should be in mode, widescreen mode. Okay. Here we go. All right. So the question is about this capital V, right? So yes. So this capital V in the branching factor. So is it okay? Let me read again the question. So it's about this part, the cutoff, or it's about the general V. Let me understand better the question. So okay, chat. Yes. So the realization of the branching factor. Yes. So this capital V is the modulus. Okay, it's the modulus of the bold vector V bar here. Okay, so those are moduli. Okay, so both V bar and V are not bolded; they're just italic, and the reason is that those are modulus of respectively capital V bar and capital V. So those are 3n dimensional. So the modulus in the 3n dimensional space, and so they are made of components V1, Vn, or V bar 1, V bar n for each electron in the system. And the vector V1, V bar 1 is given by this relation here. So V bar 1 or V bar I is damped by this prefactor. Each component of V bar I is damped by this prefactor here. So it's a component by component damping, if you like, or more than damping is basically it's a cutting off of the components Vi for large values, Vi values. And so those are, so capital V is the collective vectors including all n single particle, single electron vectors. And the one in the branching factor is capital V italic, because it's the modulus of the capital V vector of the collective n velocities. But yes, so those are drift velocities, the moduli of drift velocities. Is it clear? Is it satisfactory, the answer? And the point is that, yes, so the point is that this V bar over V has the same, compensates exactly the divergence of the local energy on the node. So I don't know if there are other questions.
Well, for the moment, there are no other questions in the chat. So I think we can proceed with.
Okay, let's proceed. Let's proceed. So let me just before introducing the power method, let me just recap what is the difference, if you like, between the variation of Monte Carlo we have seen the first day and the diffusion of Monte Carlo we have seen today. If you like, in variation of Monte Carlo, the distribution function we'd like to sample is given, this phi of r, which is given by the psi modulus squared normalized. And we construct, if you like, the transition matrix M such that the Markov process built upon the transition matrix satisfies stationary conditions where the stationary state is the target distribution pi. So we construct M based on the detailed balance condition. M was P in my previous slides here. Okay, so sorry for this misleading notation. In the DMC instead, we don't know the target distribution pi of R, because this will be the product of psi trial, which is known, and the projected psi, which is unknown. Okay. On the other hand, we construct the matrix M based on the green function, on the approximately green function, so that's the difference between DMC and VMC. In VMC, basically, the target distribution is known, and we construct M such that we're going to sample pi. In DMC, the matrix, the diffusion drift branching process is known based on the Hamiltonian, and we construct the M, the process, such that we're going to sample the unknown distribution. Okay. Anyway, so let's go ahead. So now let's go and see the other approach to project the initial guess, the initial tri-wave function to the ground state, or to the fixed node ground state, as we have seen, because we're going to use always the fixed node approximation. So in this case, we'd like to change the projection operator. Instead of using exponential of minus tau h, we're going to use the lambda minus h operator. And as before, we're going to apply iteratively the lambda minus h operator many times to the initial state, such that at the end, for an infinite number of applications of lambda minus h, we're going to converge towards the best fixed node ground state. So you see here that the projection operator is the power of the Hamiltonian. That's why it's called power method. Okay, and even in this case, you can show that applying many times the lambda minus h on the initial state, this will have as effect the outcome will be filtering out high energy states and leaving only the lowest one. So how to show this? So again, if you like, the proof goes in the same way as previously. Here, you so what you do, you develop lambda minus h as again density matrix weighted by the eigenvalues of the eigenstates in the density matrix, and so you have a sum over the eigenvalues of the system by constructing these in terms of eigenvalues, and so you have so you have prefactors lambda minus ei to the nth power, and you can factor out the one involving the ground state energy E naught, and by factoring this out, you get the component, the ground state component, plus plus something else, and this something else is weighted by lambda minus ei divided by lambda minus e naught to the power n. Okay, where now ai are the overlap values between the initial gas psi trial over psi I. Psi I is the eigenstate of Hamiltonian. So so you see here that the other terms, the other components, the higher energy components of the Hamiltonian are weighted by this prefactor here, and this prefactor here we should set lambda such that this prefactor, the ratio is smaller than 1, such that if we power this to the nth power, this will go to 0 for n going to infinity. So the condition which will lead to an argument less than 1 will lead to a condition for lambda. So lambda should be greater than Emax plus E naught half, where Emax is the largest eigenstate of the Hamiltonian, and E naught is the lowest, the ground state Hamiltonian. Okay, so if lambda is larger than this value, then the power method, by applying it, by applying lambda minus h many times, will filter out those higher energy states, and you'll be left with the ground state times A naught times the overlap between the ground state and the initial psi trial. Okay, again, as before, to get to the ground state, the initial psi trial should have a non-zero overlap with the true ground state. And at variance with the previous approach, we have to tune somehow lambda such that to a large value, to a value which is as large as the half of the highest eigenvalues Hamiltonian. While before, remember that we had an energy shift which was set to the ground state energy. So this large value of lambda can be a problem in principle, but we'll see later that this won't be really, so we will overcome this problem. Why this could be a problem? Because if we'd like to apply this approach to ab initio Hamiltonian, the ab initio Hamiltonian can have eigenvalues unbounded from above, so you can have very large eigenvalues. So in practice, you can have, I mean, the continuous part of the spectrum of the ab initio Hamiltonian can have eigenvalues diverging in magnitude. So this approach requires implicitly, if it's applied in this way, that the spectrum Hamiltonian is bound both from below and from above. Otherwise, Emax would be infinite here. So and lambda also will have to diverge. So we're going to cure this issue later. So I can anticipate that this power method can be applied also to ab initio Hamiltonians as well, not be bounded from above. So, but anyway, so it's good to recall that a care must be taken to set lambda properly, such that lambda minus h to the power n will act as a projection operator. Okay. And so now let's start from a lattice Hamiltonian. Okay, so the lattice Hamiltonian is regularized such that you don't have the problem of Emax, diverging Emax. So this will have a spectrum which lies in the finite energy range. Okay, and so the lattice Hamiltonian will have a kinetic term, a hopping term between sites, and potential term which can be expressed as a density operator. Okay, so now if we'd like to apply the power method on a lattice, we can describe the propagator now is not E2 minus tau h, but is lambda minus h. Okay, and that's the propagator, the green function, our green function, and lambda is diagonal term. Okay, so the Hamiltonian here will have both diagonal, the potential, and off diagonal terms, the kinetic term of diagonal. And so in general, this can be written as lambda diagonal, so diagonal term delta x prime minus hx prime, including both diagonal and non-diagonal elements. And as we have seen before, for the diffusion Monte Carlo, we are going to use an important sample, the green function, where now the bare lambda minus h operator is multiplied by the trial wave function psi g. So here is not psi t, but it's psi g. Again, I mean, so the notation could be misleading, but keep in mind that psi g now is the trial wave function. Okay, the reason why I call it psi g is because it's called also guidance wave function, not only trial. But anyway, so this is the initial guess we have to make this simple. That's the initial guess we have in our for our system. And also notice that the important sampling is such that the ratio is between the initial wave function at x prime and the initial wave function at x, between the x prime and x coordinates. So what we'd like to know, we'd like to know how to build a diffusion process out of this lambda minus h approach. Okay, so and the diffusion process is built upon a normalized distribution, a normalized transition probability, which is given by gxx prime divided by the normalization of this probability. Okay. And so again, as before, as in diffusion Monte Carlo, here we have to find a stochastic process based on the green function. So the green function will define a transition probability which will let my my particles, my electrons, diffuse. Okay, so here the normalization at the denominator, if you sum over x prime, gx prime, you realize that this sum over x prime of gx prime is nothing else but lambda minus the local energy at x. Okay, so the first term is easy to get, the delta function. So you sum over all possible x prime, and you get also x prime equal x, and you pick lambda. And the second term here, so the sum over x prime of x prime, hx prime times this important sample factor, this will lead to the local energy. And maybe it's worth explaining you why I get the local energy here. Okay. Okay, so so I get my important sampled green function g x prime equal to psi trial x prime over psi trial x times lambda delta x prime minus h x prime, right? Now, if I do this, I sum over x prime g x prime, I get lambda, the first term, and the second one is what is sum over x prime h x prime psi trial x prime divided by psi trial x. Okay, so this one is the local energy EL of x in the lattice notation. In the okay, so now how can you show this? So remember the local energy we defined the first day at a given configuration x, okay, was equal to h psi trial x over psi trial x, right? So now it's very easy to understand this relation because you can you can insert a resolution of the identity. So first of all, I need to define what is psi trial x in this basis set. Oops, can move these. Let me see if I can move these around. Should be easy. No. Okay. Yes, this way. Okay, so what is psi trial x in this notation? I can write this formally as bra psi trial ket. Okay. Now, what does it mean when I apply h to psi trial? I apply this operator to this state here. I can include a resolution of the identity x prime bra x ket x prime bra psi trial and so so my H psi trial X, his notation is X H psi trial. And now if I rewrite H applied to psi trial in this way here, I get sum over X prime, X, H, X prime, X prime, psi trial, and so this is equal to sum over X prime, H, X, X prime, psi trial, X prime. Okay? And so indeed, the local energy at X, so it's H psi trial X over psi trial X, is nothing else than sum over X prime, H, X, X prime, psi trial X prime divided by psi trial X. So I showed you that the lattice, the local energy, is indeed written in this way here. Okay. So if I go up, then this is exactly the one I've written here. So, so sum over X prime of Gxx prime is equal to lambda minus ELX, the local energy. Okay. All right. So let's move on. So now I normalized my propagator, my green function, Gxx prime, to get the transition probability Pxx prime, but then this factor here, the denominator used to normalize Gx prime, becomes the weighting factor of my walkers. So if I move from x to x prime according to this Px prime, the normalization factor used to get this Gx prime probability should be compensated by a weighting factor the walker will acquire, and the weighting factor is the one I use to normalize the green function. And so by moving from x to x prime, the walker will pick up a factor lambda minus the local energy computed at x. So you see that on this framework, the diffusion weighting process is very transparent. So it's very, very elegant. The weighting factor arises as a factor, a normalization factor for the transition matrix. So this elegance is also will be also exploited to extend the power method non-lattice to the continuous, and this will be done in the next slides. But before going to the continuous generalization of the power method, and this will define at the end the lattice of regularized diffusion Monte Carlo, before getting into that business, I'd like to mention what is the fixed node approximation in this framework, okay? Because when I defined the transition probability in this way, I assumed that all gxx prime would have a positive sign, but that's not true. Due to the fermionic sign problem, some g of xx prime won't have the positive sign, will have negative sign. So it won't be possible to define a good transition probability. So how to solve these problems? We solve this problem by introducing an effective fixed node Hamiltonian. Okay, so the effective fixed node Hamiltonian is such that the matrix elements of H are the original matrix element. So the matrix element of the effective H are the original matrix elements of the Hamiltonian if the corresponding gxy is positive, is non-negative. Okay, is positive definitely. In case the gxy are negative, the corresponding matrix elements of the effective Hamiltonian are set to 0. Okay, but at the same time, those elements set to 0 in the non-local part of the Hamiltonian are summed in the diagonal term. Okay, by adding to the diagonal term, which is the potential, an additional contribution, which is called the sign flip term. And the sign flip term is equal to minus the sum over y of gxy only for those gxy which are negative, because those are not good for a definition of a diffusion process based on the green function lambda minus h. So those will be summed up in the diagonal term, in this sign flip term. Okay, so we modify the structure of the Hamiltonian. So we modify the off-diagonal elements by keeping only the off-diagonal elements which provide positive gxy elements, and those elements which are affected by the same problem, which will lead to the same problem, are set to 0, while they are summed up in the local potential. This change from H to H effective, where the H effective has 0 elements leading to negative G, and adding the local potential with the sign flip term, this Hamiltonian can be shown to provide a ground state wave function whose energy is an upper bound of the true ground state energy of the system. Okay, so and the proof goes in this way. So you can show that the expectation value of the Hamiltonian on the ground state of the effective Hamiltonian is less equal than the ground state energy of the effective Hamiltonian. Okay, and so this implies automatically that the ground state energy of the effective Hamiltonian is an upper bound of the true ground state energy, because this expectation value is also an upper bound of the true ground state energy. So it's a chain. It's a hierarchy of inequalities, which basically guarantees that the ground state energy of the effective Hamiltonian is an upper bound of the true ground state energy, or the ground state energy of the true Hamiltonian. You see here that the fixed node approximation is also beautifully, if you like, formalized. It's not a constraint in the diffusion. I mean, this will imply also constraint in the diffusion, but it's reflected automatically in an effective Hamiltonian. While in the diffusion Monte Carlo algorithm, the effective Hamiltonian was kind of hidden behind the fact that we were constraining the diffusion with null pockets. Here we really have a transparent modification of the Hamiltonian, such that we defined an effective Hamiltonian having good matrix elements. So I found this again much more transparent, if you like, in terms of formalism than diffusion Monte Carlo. Okay, so now, is it clear to everybody all these steps or not? I mean, this fixed node Hamiltonian approximation on a lattice. Is it clear, or do I need to maybe specify something more? I don't know if you can see any chat here. There is no reaction. Anyway, I invite you to interact as much as possible, such that I can understand if you are following me or not. Anyway, so so we defined an effective Hamiltonian, which is upon which we can define a diffusion process based on the Green function lambda minus h, which is positive definite. And we have also the other properties, the effective Hamiltonian as a ground state, which is an upper bound of the true ground state of the true Hamiltonian. So let's go ahead. So I told you that at the beginning that we could have the problem of defining the proper lambda in the lambda minus h Green function. And so lambda must be larger than Emax plus E naught half. In the case of Emax diverging, in the case the spectrum is not bound from above, we are in trouble, apparently. But there is a way out. The way out is to take the lambda infinity limit of the Green function. So we'd like to devise a formalism where now the Green function is evaluated in lambda, in the limit lambda going to infinity. So in this limit, I can G again becomes gets a form which is quite close to the form used in diffusion Monte Carlo, because I can factor out lambda And then I get 1 minus h over lambda by factoring out lambda here. And if I replace 1 over lambda by delta tau, by the time step tau, we can call it delta tau or tau, whatever, the time step tau, this you can recall, you can rewrite this as an exponential of minus tau h. So this is very close form than the one we have seen for the diffusion Monte Carlo, where we got exponential minus tau h minus et. So we're going to use this replacement. So 1 over lambda equals the time step. And in the limit of lambda infinity, the time step is going to 0. Okay? So so what is the problem of keeping explicitly a very large lambda? The problem is that the probability of staying the same lattice configuration or electronic configuration X is getting large as lambda grows. Okay, so I can write this down actually, for this will be more, I think, more clear. So so let me see. So we have this, so Jx x prime normalized, right? This is my probability of going from x to x prime. Okay. Now recall that Gx prime is equal to lambda delta x prime minus h x prime psi trial x prime divided by psi trial x. Now, what is the probability of staying on a site? So this probability of jumping from x to x prime, right? This px prime. But I have also the probability of staying. The probability of staying is pxx. And what is pxx? Pxx is given by lambda minus hxx. Okay, but in the limit of lambda going to infinity, pxx is also going to infinity. Okay, so I would have basically I would if I would simulate this stochastically in a dumb way, I would spend a lot of time staying at time x, and at every time step, at every application of my green function, I will stay a lot of time in the same configuration, and I will never move. I mean, I will move very rarely. So my chain will be x, 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 and then I jump to x prime, but then I stay to x prime many, many times, and so on and so forth. So this will be my chain. So I'd like to estimate, so what is the way out? I'd like to estimate the residence time. Okay, I'd like to estimate how long I will stay in a given configuration in advance, without simulating explicitly by iterating for all time slices. Okay, I'd like to have the estimate of a residence time at a position X. Okay, such that when I jump here, I have this estimate. I just evolve all the weights for this time, and then I can jump direct there without waiting too many iterations. Okay, so this is the idea. So how to estimate this residence time? So, okay. So to estimate the residence time, I can write it down. Okay, I can write it down in this way. So, so I define first the probability of leaving. Okay. So, and probability of leaving Q is equal to Q of X, because it depends on X, on the actual position, is equal to the sum over X prime different from X of G X prime divided by the normalization condition, which is lambda which is lambda minus EL of X. Okay, so so do you understand why I'm defining this probability of leaving in this way? Because I'm summing all events, all probabilities of just changing the configuration. Okay, right? So if you like, okay, so you can see also this as probability of leaving as 1 minus probability of staying. Okay. So anyway, so the real staying is the diagonal one. So the probability of leaving is the sum of all of diagonal terms of the transition probability. Okay. Okay. So now let's ask what is it now, given the probability of leaving Q of X, let's ask the question, what is the probability of leaving the site X after k iterations, k applications of the G green function. So the probability of leaving after k iterations is this one. Of leaving after k iterations. Okay, so it's I call it T of K, and it's equal to the probability of staying for K minus 1 iterations, right? Times the probability of leaving at the kth one. So this is the probability of leaving after k iterations. All right? I know Q, right? Because Q is given by this expression here. And so I can, in principle, sample K. So I know a priori what is in advance what is the distribution. I can sample K according to this distribution here. So remember the first day we have seen together the inversion method was one of the method to sample a random number from a given distribution. And this is a nice application of the inversion method used to derive this lambda, infinite lambda limit of the power method. So we'd like now to draw K according to T of K. Okay? And so remember how to do that, right? So we have seen this the first day. So you should compute the cumulative distribution of T of K. Okay? And so you should compare this with then the random number. And a random number generated from 0 to 1. So you should compare the cumulative distribution, sum over K from 1 to K tilde of T of K. And this one should be compared with the random number Chi, for instance. So by inverting this relation, we'll be able to draw K according to this distribution here. So now I should remind you that this should be normalized, right? This should be normalized, but this is already normalized. So the T of K is already normalized. So so you can do the math and you can get the sum over K from 1 to K tilde. So this is sum over K from 1 to K tilde of 1 minus Q to K minus 1 times Q. And this one is 1 minus Q to K tilde. Okay. So you can see here that this is already normalized because this implies that sum over K from 1 to infinity, which is the normalization of T of K, this is equal to 1 already. Because if you send K tilde to infinity, this goes to 0 because 1 minus Q is less than 1. So this is already normalized. And so we can directly compute this relation here. We can directly invert this relation here. Let's do that. Okay, so I should change page. Oop. Should add a new page. Page 2. Let me see. Hmm? What? I don't know why it's not it's duplicating here. Ah, pages here. One. Yes, sorry. Good. Okay. Oops. Too many. Okay. All right. So now let's compute. So yeah. So we should invert that relation, right? So what we got now the sum over k from 1 to k tilde of the probability of living at the k iteration is 1 minus q to k tilde equal to our random number chi. So we should invert this. So you get 1 minus q to the k tilde equal to 1 minus chi, which is anyway another random number from, so chi is homogeneously distributed from 0 to 1, and 1 minus chi is by definition, I would call it R, which is still homogeneously distributed from so this will be is also distributed from 0 to 1. Okay. And so now we take the logarithm of both sides, and you get k tilde equal to logarithm of r divided by logarithm of 1 minus q. Okay. Remember what is q? So q, what was q? Remember what was q? Q was this one, right? Q was this this element here. Okay. And so let me see if I can copy this. Let me see if I can copy this. Actually, page. Okay. So Q was that one, right? So I can rewrite it here. So Q was equal to sum over x prime different from x of gxx prime divided by lambda minus the local energy. So this, for lambda going to infinity, okay, this is of the order of the leading term is 1 over lambda sum over x different from x, so the probability of leaving of gxx prime. And so as 1 over tau was 1 over lambda was my time step, this is tau sum over x prime of gxx prime. Okay, And so you see that lambda is infinitely small in the limit of, sorry, Q is infinitely small in the limit of lambda infinitely large. Okay, so then I can say, this is much smaller than 1Q. So it means I can expand this relation for small q, and I get minus log R divided by Q. Okay, so, and this is what? This is by plugging Q here in this relation. I plug Q here in this relation. This is minus log R divided by tau sum over x prime different from x of g x prime. Okay, and so I got this relation, and I can go further. I can make a step further, so I can multiply now both left hand side, right hand side by tau, and so I get the final relation, which tells that tau times k tilde is equal to minus log of R divided by sum over x prime different from x of g x prime, with R a random number with a random variate homogeneous from 0 to 1. And why I've written this relation in this form here? Because now tau in the limit of lambda infinity, tau times k tilde is what can be seen as T res, the residence time. Okay, because tau times the number of steps is exactly the residence time I was aiming to get since the beginning here. I was aiming to get the residence time as how many time steps I have to wait before leaving the configuration X. And so this in the limit of lambda infinity, this becomes a continuous formulation where now I know exactly how long the walker will stay in the site X, because this is a quantity local at a position defined by the position X. Okay, so so this is very, very nice. So I'm able to write down a continuous formulation. Okay. And what are the weights in this continuous formulation? In this continuous formulation, so I know how to deal with the diffusion process, because I know the residence time. I know how to leave after T-res, and the weights will assume the exponential form e to minus T residence times the local energy of position X, normalized, shifted by a shift which will prevent a rigid shift, the constant. which will prevent underflows or overflows of the weights. Okay, so let me go back to the slides. Okay, yeah, so that's basically summarize what we found. Okay, so that's the probability of leaving, and that's the residence time minus log R divided by the sum of the octagonal terms of G. Very nice. So I solved the problem of a spectrum of H unbounded from above, and so I can hope to apply this also to the continuum case, not only to the lattice case, but also to the continuum case. So what are the advantages of the power method? The effective fixed Hamiltonian is beautifully defined. So it's we have an operator which is defined in a very strict way, and this will avoid divergences of the drift velocity, because we don't have drift velocity. We just have hopping elements weighted by the green function. There is no time-step error because we are in the continuous time limit formulation. So this lambda infinity will lead to a continuous time limit formulation. And also there is a possibility of including non-local operators, because not only the hopping term, but like in the lattice Hamiltonian, the kinetic term, but also other operators can be non-local. And one family of operators which are non-local and are relevant for our ab initio formulation are the pseudopotentials. Pseudopotentials are by construction non-local. Why they are non-local? Because they are written in this way here. So the pseudopotential is written as a sum over channels, those are angular momentum channels, plus also a local term which is always present, but the non-local part is expanded in angular momentum channels over which the wave function is projected. So you should imagine that I should apply this operator to the wave function, the tri-wave function, which will have their angular components filtered by this projection and weighted by the local potential. This is a potential which is centered around a nucleus. Okay, so this depends on the given nucleus I, for instance. Okay, so xi is the difference, if you like, is the distance between the electron I and the nucleus, capital I. Okay, so that's the distance between electron nucleus distance, this x. And so the non-locality is exactly given by this projection operator over angular momentum channels, and there are different ways there is a particular way of projecting this over angular momentum channel using an explicit integration over a sphere centered on the nucleus. So this is necessary, this explicit integration by quadrature rule, because we are dealing with a many-body Hamiltonian. So in the case of single-body Hamiltonian, you could much more easily project this according to the angular momentum components of the one-body wave function. But as we are dealing with a many-body wave function, we should project this numerically using an angular integration over on a sphere centered on the nucleus. And this is done by quadrature rules. Okay, it's like Simpson, but Simpson applied to angular momentum integration. I'm gonna go back to this point later. But anyways, just to show you the advantages of the power method on a lattice, and then we're gonna try to extend the lattice into the continuous space. So hopefully you appreciate the beauty of this approach. Could we apply a lattice scheme on the continuous? That's the question, right? So could you extend this to the continuous case? Okay, because so far we talked about sites and the possibility of hopping from X to X prime. The possibility of computing the probability of hopping was transition probability was basically done thanks to the fact that I had a sort of finite number of X prime site accessible from X, such that I could, in principle, apply the heat-bath algorithm to go from X to X prime. So how to construct this transition probability from X to X prime on a continuum? So to construct this probability on the continuum, we should discretize the kinetic term. So the first step is the discretization of the Laplacian. So the Laplacian, that's the one dimension, that's the Laplacian in 1D. The Laplacian in 1D can be discretized in this way by finite differences, and that's a formula which will have an error of the order of a square, where a is the lattice, is the mesh size of our discretization. So you can see this as a combination of translation operators. Okay, so if you apply this to a function f centered at x, this will lead to finite differences of the function f computed and translated positions in this way. So it's like translate operators applied to the function with given sequence of translations. And you can see, you can immediately see that now the Laplacian implies that the discretized Hamiltonian will have finite elements connecting x with x plus a, or x and x minus a, because it's exactly the action of the Laplacian discretized. And this is a general formalism for the general case. So for each particle and for each component, you can have this formulation, this discretization of the Laplacian. So this applies to the 3n dimensional case. Notice that now the hopping terms, because those are effective hopping terms on the continuum, acquire a prefactor which is 1 over a squared, where a is the mesh used to discretize our Laplacian. Okay, so here you can also be more flexible, if you like, in the definition of the discretized Laplacian. You can also imagine of including 2 meshes and to discretize the Laplacian with two steps, A and B, such that the respective weights sum up to 1. Okay, so you can even imagine to include more than 2 meshes for the Laplacian discretization. And you have a flexibility of discretizing Hamiltonian, with the only requirement, which is very important, that that in the limit of small a and small b, you should recover the Hamiltonian of the continuum, because we are interested in computing the ground state energy of the Hamiltonian of the continuum. So we should have a way to control this limit in such a way that the effective Hamiltonians, the discretized mesh, will tend to the true Hamiltonian of the continuum. So at the beginning, we thought about this 2 mesh trick to make the sampling of the continuous space ergodic. Okay, so because if you discretize the Laplacian by just 1 mesh, which is rigid, then your particles will move on a grid which is defined by your lattice space A, and they will never explore other regions of the continuous space which fall outside this mesh. While by applying the second grid, and if the mesh, the step of the second grid is incommensurate with respect to the previous one, by applying randomly either one or the other mesh, your particles can explore the full continuous space. And this is nicely illustrated by the following slide, the following animation, where in the first situation, just one mesh. In the case of 1D system with 2 electrons up and down. The 2 electrons are the red balls, which are moving, which are hopping according to the discretized Laplacian through the diffusion green function G. In one case, you just have one mesh with fixed length A, and the other case, we have 2 meshes with the one being incommensurate with respect to the previous one, so B square root of 5 times A. And so you can see here that by defining a random walk driven by the transition probability with two meshes incommensurate, your walkers will explore the continuous space, at least much more densely than the previous one, where you have stronger ergodicity problems. Okay, so our discretization should also be compliant with the ergodicity of the continuous space. Another way to be compliant is to use a single mesh, but where the orientations of in 3D are basically random. So you can in that case also, it's a way to explore in an ergodic way the full three-dimensional space. Okay, so now this 2 mesh trick to sample the continuous space has been recently improved, further improved by Kozuke and Sandro in a very recent publication, where this double mesh trick to sample the Laplacian, to represent the Laplacian, has been used to effectively sample different energy scales in the case of heavy atoms. So imagine you have heavy atoms, you have core regions, you have semi-core regions, you have valence regions, and you can, those have different extensions, and the diffusion process driven by a sort of adaptive mesh will sample much more effectively the shell structure of the atoms, particularly in the case of heavy atoms, where you have several shells of different length scales. And so the sampling of the configuration space of electrons using this double mesh has proven to be much more efficient than the previous the single grid. So you have a speed up, enormous speed up for heavy atoms of 1 order of magnitude, even more. Okay, so this is to tell you that another advantage of using this approach is also to speed up the diffusion process, where you have several length scales in your systems, and this is something again, another advantage with respect to the standard diffusion Monte Carlo, where now in the diffusion Monte Carlo you don't have the possibility of implementing this adaptive sampling strategy, because your diffusion Monte Carlo, your diffusion step is mainly driven by the variance set by your time step. So this approach adds further flexibility in order to sample different length scales in a system. Okay, so, but again, that's very nice. We should require anyway that this discretized Hamiltonian is representative of the true one in the continuous time, in the continuous space limit. Okay, so for the lattice space going to 0, this should be representative of the true Hamiltonian. And so to cure the, I mean, in other words, we'd like this convergence to happen for the largest A's possible. Okay, so we'd like the behavior of the energy as a function of A to be as flat as possible around A equals 0. And to make this as fast as possible, such that we can use quite large lattice spaces, we modified further the effective Hamiltonian such that the local energy of this effective Hamiltonian is equal to the local energy of the continuous Hamiltonian. Okay, and so you realize that the missing ingredient to get this equivalence is in the local term the difference between the Laplacian, discretized Laplacian, and the continuous Laplacian. So those localized operators included in the local potential will make the local energy of the lattice Hamiltonian or the discretized Hamiltonian equal to the local energy of the continuous Hamiltonian, and this will speed up enormously the convergence in the lattice space. So I can skip this because it's too technical, because I'm running out of time. So, so this is basically the algorithm, okay? That's the lattice regularized diffusion Monte Carlo algorithm. So we start from a configuration A, X, weight W, and time T. So we, given X and the Hamiltonian, we have a finite number of X prime connected to X through the discretization of the Laplacian. And from this finite number of X prime, through the hit-but algorithm, I can select the most likely one for the particle to jump. And this is, and basically this will define my diffusion process of my random walk. Am I muted or not? I'm still, hopefully I'm still, okay. And before moving from X to X prime, I know the time of residency on X, thanks to the approach, to this infinite lambda approach I explained to you. And so having, by the knowledge of the time of residence, I can update the weight of the walker by minus tau, the time of residence times the local energy, okay, shifted by a constant which prevents, as I told you, underflow or overflow of the weights. And then the total time is updated with this time of residence. So I'm updating the total time, the evolution time. And so I end up with a new configuration X prime with weight W prime, which is a product of W times the local weight, and the time type prime. So I go through, and then after target time capital T, I can also use the branching. I will use the branching step as in diffusion Monte Carlo, and so on and so forth. So I have diffusion steps, weighting steps, and branching steps after every time capital T. Right. So let me summarize the difference between diffusion Monte Carlo and lattice regularized diffusion Monte Carlo. In the diffusion Monte Carlo, I have a throttle approximation of the green function, something I don't have in the lattice regularized diffusion Monte Carlo. On the other hand, in the lattice regularized diffusion Monte Carlo, I have a lattice space bias due to the discretization of the Laplacian, although I mean this bias is reduced by improvements in the effective Hamiltonian. So in the diffusion Monte Carlo, I have a time step extrapolation, while in the lattice regularized diffusion Monte Carlo, I have a lattice space extrapolation, and so I have you know an analogous treatment of controlling the lattice space bias as in the diffusion Monte Carlo I had for the time step by performing different simulations, different lattice space, and extrapolating for the lattice space going to 0. And that's the comparison between, for instance, diffusion Monte Carlo extrapolation and lattice regularized diffusion Monte Carlo. I'm mapping here lattice space with and time step together in this way, such that I can plot the two on the same plot, but the idea is the same. So I have to extrapolate to the projected energy. Yeah, so I mentioned about the possibility including pseudopotentials, and so in this formalism, the pseudopotentials will appear as off-diagonal terms because while in the Laplacian, the discretized Laplacian will imply translations by the lattice space vector, in the non-local pseudopotential, the application of the operator will imply rotations around the nucleus. And so the rotations as translations are non-local operations, and so those will define non-trivial, non-local elements in the green function, so non-trivial hopping terms in the transition probability. That this was a major advance with respect to diffusion Monte Carlo in the original formulation, because in diffusion Monte Carlo the non-locality of the pseudopotential was treated by localizing basically this into the diagonal term. So all non-local terms were put in the local potential, while in our case those non-local terms which have the right sign, which are compliant, fixed and not compliant, will be treated as diffusion terms. And so and those diffusion terms actually are those terms which will make the walkers escape from strongly negative regions in energy around the nucleus, which will cause wide fluctuations in diffusion Monte Carlo. So the message here to take is that in the lattice regularized diffusion Monte Carlo, the inclusion of non-local pseudopotentials is much more stable than in the standard formalism of diffusion Monte Carlo. And so this opens the way of applying diffusion Monte Carlo in a very general ab initio Hamiltonian, where usually pseudopotentials are necessary to speed up the calculation by getting rid of core electrons. So yeah, so I'm almost done basically. I'd like to recap a little bit the approach, if Sandro and Kosuke agree with me, of I mean, just, you know, the workflow of Kosuke was very clear in explaining all the workflow, but just to give you a slide how the ab initio quantum Monte Carlo approach works in practice. So from the DFT, we generate condition orbitals. The condition orbitals define the variation wave function. We optimize the wave function by using the methods Sandro explained to you yesterday, actually. And once you get your best variation wave function, then you can switch on the projection towards the ground state or towards the fixed ground state, which further lowers the variation energy and gets to the best possible representation of the ground state given the nodes imposed by the variational wave function. So by optimizing the wave function before getting to the guess, what's called psi trial in my slides, to get the best psi trial is useful through the optimization. This part one is useful for two reasons. The one reason is that for better wave functions, you have more stable local energies through the zero variance property, and so less fluctuating weights in the diffusion Monte Carlo. And then by also optimizing the wave function, improve the nodes of the wave function. So the nodes of the optimized wave function are not closer, obviously, to the true ground state. So you improve also the fixed node energy, not only in the stochastic error bar through lesser fluctuations, but also in the bias, because you get closer to the bias is lesser because you get closer to the right nodes, exact nodes. Yeah, I don't know. Maybe I can just show up still some limitations of Quantum Monte Carlo. I mean, as theory. I mean, as a general framework. So we are talking about the accuracy, but associations have some limitations. So there are open questions still there, and those are active research directions to take. Also for you, new generations, there are challenges ahead, which they are waiting for being solved. One challenge is for if you do crystals extended systems, it's very difficult to do the extrapolation to the thermodynamic limit. So there are ways of accelerating extrapolation to the thermodynamic limit. The second one is the fixed node error. I mean, how to release the fixed node constraint to get to the true ground state energy. So in that case, if we solve the fixed node error, we would be able to get the exact solution of any electron many-body problem, and I think this will be worth the Nobel Prize. And then there is also the lack of consistency in the determination of pseudopotentials, in the sense that the pseudopotentials are generated using lower level theories like R3-Fock or like DFT, and those are not necessarily suited once plugged into a many-body framework like Quantum Monte Carlo. So the transferability of the pseudopotential, this is a problem not just of Quantum Monte Carlo, it's a problem of many ability theories, by the way. Okay, and so, but I'd like to finish by saying that the DMC is one of the most accurate, if not the most accurate ablation method, and so even for solids, not only for molecules, and so we have several papers claiming this. One of these has been published quite recently, and it shows that the formation energies of several difficult compounds are much better in agreement with the experiment than those, for instance, computed with DFT calculations. So you get the green bars are the difference with respect to the exact or the experimental estimates for the formation energy of some compounds, and you see that the error is the smallest for the green bars, the diffusion Monte Carlo green bars. And of course, it's a method which scales very well with the number of particles, also thanks to the improvements, algorithmic improvements, and also hardware improvements in GPU, for instance, mentioned by Sandro yesterday. Really can boost the acceleration and the scaling with in terms of prefactor, right? Because the scaling is theoretically determined by the operational cost of the method, but the prefactor depends strongly on the architecture where you run, and also it's embarrassing in parallel. So that's a suitable technique to run on HPC machines. And with that, I finish. So that's a list of interesting papers you can read to deepen your knowledge on this first encounter of diffusion Monte Carlo I propose to you today. And the last but not least is the paper by is the book by Sandro. Okay, so with that I'm done. So thanks for listening, and now I'm ready to take your questions. I guess I'll get a lot of questions from your side.
Okay, if everyone has any question, please just unmute yourself and ask the question to Michele, or you can write it in the chat if you want.
Okay, so
okay, I can see that there are no questions.
Everybody's tired.
Yeah.
So hopefully the next time this will be done in presence. So I'm gonna see your faces and see whether you're still alive or not. Because
yeah, let's hope.
That's
okay, everyone.
The barrier between you and me, which is the Zoom, which is at the same time a barrier and the link. So, but we should cope with this.
Yeah, I agree with you, Michele. Okay, so if anyone has any question, or we can just go for the lunch break, and let's come back at 1:30.
Okay.
Bye, everyone.
See you. Bye-bye. Bye-bye.
Okay, I think we can start. Okay, welcome back, everyone. Thank you to be here to the third lecture of the day. We will have a presentation made by Kozuke Nakano. And Kozuke, the floor is yours if you want to share your screen and start your presentation whenever you want.
Okay, can you hear me?
Yeah, very well.
Also, okay, okay. So, and you can also see my screen.
Yeah, absolutely.
Okay, so shall we start? So welcome back. So today, followed by Professor Kasura presentation, I will explain details of lattice regularized diffusion Monte Carlo implemented in TurboRVB. Okay. So today is the final day of the tutorial. So today we will do LLDMC calculation with the optimized wave functions for the three compounds: hydrogen, the hydrogen dimer, and carbon 2 dimer, and the hydrogen 2 on graphene. So this is a typical input of LLDMC calculation in TurboRVB. This is actually the LLDMC calculation is also input is very simple as VMC calculation, but we should know the meanings of several variables. Okay, especially in this DMC LLDMC section. Okay, their variables actually corresponding to the parameters explained by Michele in this morning session. Okay, for example, this engine, don't worry, I'll explain these parameters later more in detail, but let me briefly explain, okay, them. So first, engine is the number of iterations, but here it does not mean the number of Markov chain Markov chain, let's say, the number of branchings in LDMC. I'll explain it later, okay? And also this T-bra is the projection time. So between the, let's see, the time between branchings, okay? This is E-try. E-try is the shift, energy shift for the projection to filter out, as I told you, filter out the ground state of the wave function from your trial wave function, okay? And ALAT is the grid to regularize Hamiltonian. Okay, this is also put here, ALAT. Okay, let me explain detail here. Okay, as I told you, lattice regularized diffusion Monte Carlo is a technique to filter out the ground state, okay, from your trial function. Typically, optimize the VMC, okay. Of course, as I told you, it is possible. It is possible to use DFT nodal surface without optimizing the nodal surface by diffusion variation Monte Carlo at the variation Monte Carlo level. But also in TurboRVB, we can optimize the nodal surface of the wave function using at the VMC level. Okay, and if since in this morning session, Professor Kasura explained to you, since this term is smaller than 1, as far as lambda is large enough, the projection, this power method filters out the ground state wave function from a given trial wave function. Okay, in TurboRVB, E try is the corresponding parameter. Okay, this lambda. But sorry, let's see. So this lambda is this one, okay? But in TurboRVB, we put the E try instead of lambda, and inside the code, this -2 times E try is plugged in to this lambda. So, for example, typically you can put, for example, a VMC energy for E try. Of course, DFT energy is also okay, but anyway, yeah, it is better to. I usually put optimize VMC energy for E-try. I don't think there's no problem, okay? But there's no default value, right? So you should not forget to put this E-try in your DMC calculation. And also, ALAT is the most important keyword in the LLDMC calculation. This corresponds to the discretization lattice in the LLDMC calculation, and also this is also explained in the Kasura's presentation. Since in LLDMC calculation, in the LRDMC implementation, the Toyota-Suzuki decomposition is not needed. Different from the standard DMC framework. So the so-called time step error does not exist in LRDMC. Okay, but instead this ALAT, we call this lattice. We call this lattice space error. Okay, exists instead in the LRDMC calculation. So time step extrapolation is not needed, but we need extrapolation, ALAT extrapolation. Okay, as shown later. How to do it? There is a tool to do expression in TurboRVB. So I'll explain how to use it later. Okay, so in practice, it's very important to understand the fixed node approximation, the limit of the fixed node approximation. Actually, this is the schematic figure of the fixed node approximation. Okay, you are assuming that there are two nodes, let's say two nodes here in your trial wave function, and the amplitude, if amplitude is like that, even after you filter out, you apply the power method due to the limitation of the green function, let's say. So fermion, there is a fermion sign problem, so we should fix the nodal surface, okay, even at the DMC level. Okay, so I mean, your nodal surface, your nodal surface is not relaxed, but only the amplitude is relaxed. Okay, in the LLDMC framework. So it means that so optimizing the nodal surface is so crucial. Actually, they determine the final result of your LLDMC calculation. So actually, the most straightforward the simple procedure is first you do DFT calculations for generating your trial wave functions. Okay, for several. So for example, you can do the most straightforward one is you can do a DFT calculation for generating a trial function. Okay, and then you add the Jastrow factors and optimize at the VMC level. If you do not optimize the Jastrow factor, if you do not optimize this antisymmetric part at the VMC level, it means that, as I told you, the nodal surface is fixed to that obtained by DFT calculation. Okay, in that case, the nodal surface, the calculation is completely deterministic, right? Because DFT calculations are completely deterministic, so there's no okay, all the calculations are completely reproducible. Okay, but if you optimize the nodal surface also, it means that sometimes optimization, if optimization goes in the wrong direction, also your DMC as well as DMC calculation, your DMC calculation and VMC as well as VMC calculation, let's say, were wrong. So you should be careful when optimizing the nodal surface at the VMC level. Otherwise, your DMC calculation not reproducible. Okay. Instead, the Jastrow factor essentially does not play any role in the nodal surface part. So even so, for example, for an all electron calculation, whatever Jastrow factor what Jastrow factor, let's say Jastrow factors is, even if Jastrow factor is not well optimized, the DMC calculation is essentially the same. So okay, so okay, let's say DMC. So okay, I mean so the optimizing the nodal surface should be careful about that, right? Okay. So the other important parameters in the LLDMC calculation are NGen and T-bra. NGen T-bra. Okay, in TurboRVB. NGen is actually, for example, in a VMC calculation, VMC optimization, NGen means NGen is the parameter to specify the number of Markov chain Monte Carlo, total Markov chain Monte Carlo steps, right? In a VMC or VMC optimization. Okay, but instead in LLDMC calculation, NGen means the number of branchings. Okay, so this is a bit different from the VMC and DMC VMC optimization. Here, as so every NGen, and here, okay, so each worker has electronic positions and weight. Okay, weight. So, and weight and electron position is updated during these branchings, and when, for example, here, according to the weight, weights that workers have, some workers are killed, but some workers are duplicated. Okay, so copied like this one according to the weight. Okay, this is very important, as Professor Kasura told you, to realize a very stable calculation in LLDMC framework. Okay, so and T-bra is the parameter to specify the time steps here between two branchings. Okay. As I told, as already explained, the per method is essentially consistent with this exponential form in the limit of n going the number number of iterations going to infinity. So in TurboRVB, we should specify this t bra instead of m. Okay, and in practice, if you use too small n t bra, the weights are not updated. So this is not does not make sense. Okay, in the LRDMC calculation, LRDMC calculation. Okay, but instead, on the other hand, if you use too large t bra, it means that okay, only few workers survive. Okay, so which makes your LRDMC calculation very unstable. So you should check the number of survived workers. Okay, survived workers in your between, let's see, branchings. Okay, so this can be checked. This can be output in your LRDMC output. The keyword is average number of survived workers. Okay, you should grab this keyword and then check the percentage, okay, of the survived worker. We recommend that it should be, let's say, more or less 90%. If, for example, if it is 50%, your simulation is a bit is not efficient and should be unstable. So in that case, you should decrease t bra to increase the number of averaged, okay, survived workers in your LRDMC calculation. Okay, and after as the same as in the VMC calculation, the output of the LRDMC calculation does not include any information of the total energies that you are interested in, also forces. Okay, so this can be also done by using external script, using the external script, which is called forced.fn.sh. Okay, and there are four input variables, okay, bin and core, for int and puree. Okay, so bin, actually the three of four parameters are the same as in the VMC calculations. Okay, VMC calculation. Okay, so one bin is the number of reblocking, okay, binning size, and init is the length of equilibration steps. Okay, also in the LRDMC calculation, it is better to disregard the first equilibration steps. Okay, this is init times bin minus 1. The puree is the ratio of the puree term. Okay, 1 is always okay. And actually, the new parameter is correcting factor, which is okay. So in LRDMC calculation, to realize, let's see, more stable calculation, TurboRVB, the average weights after the branching, okay, are stored to fault 12, okay, and then the average is set to 1 for all workers after each branching. Okay, here, for example, after, so in the naive implementation, the new weight is set to the average of all the weights of the workers. But in TurboRVB, so after calculating this one, this average value is stored to fault 12. Okay, so to retrieve all the weights, you should specify, okay, how many the averaged reset weights to retrieve when calculating this force. typically it is not. It typically, for example, for 5 or 10 is enough, but you should check the convergence. This false fn.sh provides us all the, let's say, anyway, yeah, by changing this correcting factor, you should check the convergence, okay, to get the converged energy. Okay, also okay, also forces can be calculated at even at the LRDMC level. Okay, one of my students asked me at yesterday's session, yes, what force actually whether or not the forces are calculated at the LRDMC level. The answer is yes. Actually, TurboRVB implements force the force calculation even at the LRDMC level, but the problem that there are a lot of actually this is not exact expression. So the so-called Reynolds expression is implemented in TurboRVB, but the problem that yesterday, as I told you, in the QMC calculation, potential energy surface is not necessarily consistent with the forces, right? Actually, this is the situation. The situation is worse in LRDMC calculation. Okay, this as the so-called Reynolds expression is just an approximation for calculating LRDMC forces. So actually, I have tried to calculate potential energy forces of some dimers, but the potential energy surface is not consistent with the forces at present. So actually, it is possible, but do not use, let's say, at present. So you should. It is better to use your VMC forces when calculating force. Okay, at the QMC framework. Okay, and maybe this is the final slide, I think. Okay, so for as Professor Kassura told you, and as told you, so there's no time step expression, but in our LRDMC calculation, we should extrapolate the energies with respect to A, the lattice space. Okay, the discretization is order of 1 over A squared. So also the error is order of 1 over A squared. Okay, this ALAT extrapolation can be done by this with this FAN VSAX binary. For example, here this is a typical example. We should specify here. We should put ALAT value and energy and this error bar of the energy, okay, LRDMC energy. Actually, this unfortunately we should put this value, actually this file by hand at present after doing this force FNSH, okay, and then here by using this one we can do, for example, quartic extrapolation or quadratic extrapolation. And for example, here E0 is the extrapolated value. Okay, FAN VSA provides us this E0 with some error bar. Okay, E0 and these coefficients with error bars. Okay, so so we should, for example, when calculating some binding energies, you should use this E0 instead of E. Because sometimes the binding energy different. Actually, the binding energy depends on ALAT this space. So it is better to do. Actually, we should recommend. We recommend you should do extrapolations. Okay, to get a correct energy, ground state energy. Okay, but the point is that one of the advantages of LRDMC calculations compared with the standard DMC calculation is that the extrapolation behaves very well, unlike the standard DMC method. As far as I understand, So time step expression of DMC is let's see, is not stable as is as not stable as in LLDMC calculation. Instead, it's as shown here, the expressions are completely smooth, no doubt for the extrapolated values at a equals 0. So if let's say if the expression, your expression is not smooth, maybe your input values are wrong. So we should check your input values again. Okay. That and also okay. So for heavy atoms. Actually, heavy, not only for heavy atoms, but also for light atoms, but all electron in all electron calculation case, it is better to use the so-called double grid algorithm in LMC, which can diffuse electron in a short length, by short, a lot, but in the vicinity of nuclei, but instead in the valence electron region, the electrons can be diffused by much longer lattice space, okay, which can decrease the computational cost drastically. Okay, here you should specify, actually you do not specify the variable in detail, let's say, because according to, so you can refer to my paper, or RC decide the region in which electron, actually the electrons are treated as, let's say, core electrons, and alpha prime is the lattice space for the valence region, but alpha prime, both RC and alpha prime are adjusted automatically according to the algorithm we have developed. Okay, so that what you should do is to specify this A, the ALAT for the core region. Okay, okay, the other parameters are automatically set. Okay, so and what only the thing you should be careful is that you should put a positive value for ALAT. Okay, if you want to use the double grid algorithm. So I forgot to tell you, if you put negative ALAT, show here I put negative value, right? So negative values mean that your electron diffusion, the direction of your electron diffusion is randomized, okay, to satisfy the algorithmicity in the LMC calculation, which is very important. Okay, so please do not forget to put here negative ALAT when you want to use the single grid algorithm. Okay, if you want to use the double grid algorithm I have introduced, you should put here ALAT. You should put a positive value for ALAT, and you should use this option IES random A equal true. This should be activated only for the double grid algorithm case. Okay, so that's actually all. So shall we? So actually, some groups have to catch up to several groups, right? Advanced one. So shall we stop my presentation here, and shall we proceed with the tutors hands-on session?
May I add something? No.
Yes. Yeah. Sure. Sandro, yes.
Oh, sorry. I mean, many of you have asked the continue.
I will stop sharing my screen. Okay.
Many of you have asked to download the Turbo with the Start my video. Okay. I've asked to download TurboRVB. So what you have to do, the only requirement, since it's still not open source, but we have a private repository. So what you have to need to have is at least a GitHub account. So you can Google GitHub create account, and you can create. You go here and you create your new account. Then you have, once you have this account, you go to the keyword git lab sys. You see sign in GitLab sys here. And here you see that you appear this window. If you are a sys, you are not. You could fill in here. But here you see there is a GitHub, sign in with GitHub. Once you have the GitHub account, you click here and you put your user. Unfortunately, I've done, I would like to, I have to cancel because I have already the account in C#. Otherwise, I will be replaced with the other account. And so I think that is very simple. Once you have this, we can immediately, so if I come in the repository, oh no, it's not GitLab. Oh, this is not the right. Here. Sign in. Okay, now I'm lost. But anyway, you have you send me that you have an account. I get in the repository Mio Kosuke, and we can include you in the project. So please don't hesitate. First, make this operation, no? Sign in with the GitHub, and then we tell us what is your Git account or your user or your email that you have to use to open the GitHub. So it should be the same of the GitHub account, clearly. And then we can put, we can allow you to use this Git repository. Another thing that I have to announce is that this afternoon for the hands-on session, we have Sineca was very kind, so we have the priority queues until 7 p.m. So not only, so that people don't have to worry to rush up. If we want to continue, we can have access to this priority queue of the last day, remember, until 7 p.m. Okay, so that's all. And I can give you again.
Okay, so before we move on to the hands-on tutorial, thank you very much again to all our participants for the TREX eSchool. This will be the last lecture for today and the final lecture for the hands-on tutorial. We encourage you to come join us tomorrow for the final day. The day will start with a session focusing on the advanced topic and recent application in Quantum Monte Carlo and TurboRVB, which will be provided by our key speakers. And then there will be a quick recap and some key questions prepared by our key speakers. So please check the presentations and videos that are available on our event page now so that you can answer the quick questions that will be posted tomorrow. And don't forget that there will be a photo shoot tomorrow, photo taking. So please turn on your camera for tomorrow. And then the opportunity to download the TurboRVB will provide more information on our final message by tomorrow or later today. And With that, we'll closing this plenary session, and you're assigning the people in the respective breakout sessions. Thank you. I think my colleague Jacopo is assigning the people now.